Now that we've discussed what mechanical waves are and their various properties, it's time to start talking about phenomena that involve waves. And specifically, we're going to be looking at situations in which waves are going to actually be combining, with specifically interference and diffraction. So let's go ahead and start and say we have two strings that are being held up by two different people. And let's go ahead and look at this top string, and let's say at some moment in time, the person on the left creates a bit of a wave pulse, and the person on the right creates another wave pulse that's moving in the opposite direction and of a slightly smaller amplitude. Now what's going to happen is that these pulses are going to travel towards each other, but what happens when they end up being in the same location? Well, what we would see is that they're actually going to grow and then simultaneously pass through each other. Now let's look at another situation where we're going to have the same sort of idea here, but the person on the left is going to create essentially a crest pulse, and the person on the right is now going to create a trough pulse. And once again, these are going to move towards each other, but this time we're not going to see that the waves grow. We're actually going to see that the waves shrink when they encounter each other, and then once again pass on through. And this is a phenomenon known as interference. These waves are interfering with each other. And this phenomenon is when you have two or more waves occupying the same place at the same time. Now that can't occur with matter, but with waves that is totally acceptable. They can be at the same place at the same time, and they end up combining to form a sort of resultant wave. Now, how exactly does that combination happen? Is there something known as the superposition principle, which is really a mathematical principle, but pops up a few different times in physics, and ultimately says that when we have these waves interfering, they become superimposed. Essentially, you're placing one on top of the other, and the displacement of the medium for the resultant wave, aka the amplitude of the resultant wave, is going to equal to the sum of the amplitudes of the individual waves. So, ultimately, you've got individual amplitudes combine to make a new amplitude. Now, there are two types of interference that we need to be familiar with. The first one is known as constructive interference, and this is interference in which the amplitudes of the waves combine to form a resultant wave with a larger amplitude. So if we look here, we've got these two waves moving, these two wave pulses moving at each other. They come here, and when they reach this point, their amplitude actually becomes larger, and then they pass on through. So this only will happen if these waves are in phase. And by in phase, what we really mean is that any crests line up with crests, and any troughs line up with troughs. They have to basically match for this to occur. So what we have here is that if I have some amplitude A1 for this wave on the left, and some amplitude A2 for the wave on the right, well, they're going to come near each other, and when they constructively interfere, the amplitude of this interfered wave, this resultant wave, will equal A1 plus A2, but then they pass through each other. And there's just a couple of different points we really need to touch on here. One, these waves are not coming and then reflecting. They do not bounce off each other. Instead, they are passing through each other. That's the first point we really want to hit on here. The other point I want to hit on is it's really important to remember that what determines the speed of these waves is simply the properties of the medium. So both of these pulses are moving at the same speed. So rather than having them go in opposite directions, let's imagine that there was actually only one hand and both of these impulses were created and they were both going to the right. Now, if that happened, these waves would never interfere with each other because they're going to continually move at the same pace through the medium. One pulse can't catch up with the other one. So the only way we are going to see interference is if we either have two different sources creating different pulses moving in opposite directions, or two, what often happens is that it will be reflected off of some sort of barrier. So you have some initial wave going towards a barrier, it reflects off the barrier, and you have a second wave coming towards it, and then they will interfere with each other. So they have to be moving in opposite directions, or at least in different directions to some degree. Now let's look at the other type of interference, which is known as destructive interference, which is that the amplitudes of these waves are actually going to combine to form a smaller wave. So these are coming towards each other once again. When they get here, they equal a smaller one, and once again they pass through each other. And this occurs when the waves are out of phase with each other, meaning that you have the crest of one wave lining up with the trough of another so that they basically balance each other out. And in this particular situation, if we had A1, what we would usually write for this other one is minus A2. So that when they combine, you get the amplitude as A1 plus negative A2. So in essence, they're subtracting from each other. And as always, they pass through. Now, one thing I want to note here is that these had different amplitudes, like A1 and A2 weren't the same magnitude. If they were the same magnitude, so let's say, like, for instance, this one was just a little bit bigger and a little bit bigger, when they reached this point, it would actually appear to be totally flat for a second, as if there was no wave there at all. But keep in mind, this would only be for an instant, because then they would continue to pass through each other. And so something that's really important to note there is the fact that nothing is actually destroyed in destructive interference. Remember, these amplitudes correspond to the amount of energy that the waves are carrying, but they still are carrying that energy even when they pass through each other. Yes, it looks like it disappears for an instant, but it's only for an instant and then it once again reappears. So just keep in mind, we're not losing anything here. Destructive, that word, is kind of a misnomer. Now, before we start talking about diffraction, there's a couple of things we need to clear up. The first is that remember, this is often what the wave would quote-unquote look like if we were observing it, where we have some source here, and you have all of these oscillations moving outward from it in different directions. But this is really, really annoying to draw, so oftentimes we're going to draw these as wave fronts, just spreading out from the source, where these fronts would be, for instance, these dark ones are crests, these light ones are troughs, and they move outward radially, and really in 3 dimensions would be a spherical pattern away from the source. Similarly, if we were to like zoom in on one piece of this, we might be seeing that the waves are going pretty parallel with each other, and if that's the case, we would draw the wave fronts like so, that they're just straight lines moving all in the same direction through whatever this medium is. Now, while this seems to make a fairly good amount of common sense, that we can kind of use our ability to recognize patterns to see where the wave fronts are going, how do we know that the next wavefront is going to be another circle going out from here, or another line going out from here? What evidence do we have that that is going to continue to happen as time continues moving forward? Well, in 1678, a physicist and mathematician known as Christian Huygens, I believe he was Dutch, developed what is known as now as Huygens' principle, which was a geometrical model that demonstrates how any wave will propagate and evolve as time moves forward. So we take a snapshot of it, we can look at where it is now, and we can see, okay, this is how the wave is going to develop next using this principle. Now there's a few steps here, and they're going to seem a little weird, but once we start looking at some examples, it'll start to make a little more sense. So the first idea here is that each point on a wavefront acts as a point source, aka an individual source for a new secondary spherical wavelet that moves through space at the wave speed. The next point is that all of these secondary spherical wavelets will interfere with each other, both constructively and destructively. And 3, that the new wavefront, the new developed one, is the sum of these wavelets, and specifically the line tangent to them. It's ultimately where all the constructive interference happens. The destructive interference removes all the other pieces. Now that was a lot of jargon, so let's actually see Huygens' principle in practice. So we have some source right here at the center, and it is emanating waves outward, and as time progresses, these waves don't stay stationary, they continue to move. Well, how do I know where exactly the new wavefront is going to be? So what we do is we go through these steps. First, let's look at this outermost wavefront, and every point, and there's an infinite number of points on this line, acts as a point source for a new wavelet, aka you can really think of it as everyone acts as a new spherically radiating wave. So I'm going to go ahead and draw one of those right here. So basically we have this point source right here, and this new wavefront goes outward at the wave speed. Now what would happen is that this would happen at all of the points along this line. And you would see that some of these would destructively interfere. Basically all these parts that are facing each other, all these side-to-side parts, will disappear because they're basically canceling each other out. And what we're going to be left with is the line tangent to these points. So I would draw a new circle tangent to all of these circles, and that would be my new wavefront. Then on this wavefront, I would say, okay, we now have a new infinite number of point sources, spherical wavelets being formed on this line. I would then say, okay, these constructively and destructively interfere with each other as they grow outward, and we would say that the line tangent to them forms the new wavefront. And this would continue on and on and on until we had it basically propagating outward at this rate. Similarly, let's go ahead and look at a situation where we have a line, so these planar wavefronts instead of a spherical wavefront. And let's say it's moving to, for instance, the right in this situation. So let's look at this one right here. We would say every point on this line is a source of a spherical wavelet. These wavelets are going to destructively interfere with the ones that are directly next to them, but the parts that are moving forward in space are going to basically constructively interfere, and we're going to have ultimately a new tangent line, a new wavefront. We would get rid of these, because these, I should note, these are not real. This is just a model to help us understand how things progress. It's just a way to geometrically analyze the situation to understand, okay, what's the next step going to look like? So now, we would do the same thing on this one, get a new tangent line. We would do the next thing on this one, get a new tangent line here. There we go. Now keep in mind, you might be thinking, well, why does this tangent line not go down inside all these? But remember, there would actually be more wavelets at all of these points, and it's going to be tangent to all of them. And then we would have new ones, and then another line forming. So let's say we have a new situation. Let's say that this right here is some sort of barrier with a gap in it. This could be a wall with a hole in it. It could be a screen. It could be anything that blocks matter from going through it, and specifically blocks the wave from going through it. And let's go ahead and say that we have a plane wave, aka the series of wavefronts, all moving to the right towards this barrier. And the question is, okay, well, what's going to happen when it encounters this barrier? What's the wave going to look like on this other side of it? Well, if we look, I go ahead and say, all right, I'm going to use Huygens' principle. So all of the dots on this wavefront, I'm going to go ahead and draw my secondary spherical wavelets. And what we see is that all of these are blocked by the barrier. Well, those wavelets can't go anywhere because they're going to be reflected from the barrier. So ultimately, I really just, in this particular situation, have this one point source right here. I have the spherical wavelet. So I'd say, well, if I'm going to draw the tangent line going forward, when I would draw that, I go ahead and erase these. And we see that the wave is change shape a little bit. Now I'll say, okay, well now on this new wavefront, I'm going to draw all my spherical wavelets once again. These are all being emitted simultaneously at the wave speed. And I would say, okay, now I need to draw the tangent line to this. And so I'd say, okay, that's going to look something like that. I'll go ahead and erase these modeled wavelets, these not real wavelets. Go ahead and draw them again, draw a new one. And what I see is that I no longer have a planar wave. What's actually happening is that the wave is starting to expand out really in a curved pattern rather than a straight pattern. And this is something known as diffraction. So diffraction is the spherical bending or spreading out of a wave around an obstacle or through what is known as an aperture. And that aperture is just this opening right here. Basically, it means a gap. An aperture just means a hole, like in a camera, for instance. Now, this occurs for any wave, but it's only going to be observable. We're only going to see this effect when the wavelength is comparable in size to the obstacle or the opening. So, in other words, if this aperture was super, super, super tiny and went all the way here, we wouldn't actually see this happen. What would happen instead is that the wave would just reflect and there wouldn't be really much coming through. Similarly, if we make our aperture humongous, well then the wave is just going to go through unhindered and there's not going to be any bending. So, the key point here though is that if we have something going through a gap, or around an obstacle, and this is really going around two different obstacles, two different walls, we start to see the spherical bending around these obstacles and through this gap. Now, what are factors that affect the amount of diffraction? When we say the amount of diffraction, we mean if there's more diffraction, you're going to see more bending. It's going to become more circular. And if there's less diffraction, it's going to be not quite as circular. It's going to be a little more flat, and it's going to be a little more consistently moving forward. So you're going to get more spreading, more bending when there is more diffraction. Well, the first thing is let's talk about, like we just said a second ago, the size of the opening. That if you have a smaller opening, well, you're actually going to have more diffraction, more bending around the sides of this barrier and through the gap. And the reason for that is you were going to have fewer room for these point sources to be emitting these waves, and so these on the edge are going to basically be having a lot of curving because they're not being interfered with very much. Now, if I have a larger opening, well, what's going to happen is that you're going to have a lot more point sources, and most of these are going to continue having wavefronts that just look like the previous ones, these planar ones. Only those at the edge are going to have this bending effect, so it's going to be much less significant than it was previously. So that's the first thing. Smaller opening, more spreading, more bending, more circular moving forward. Larger opening, less of that. The other one is the size of the wavelength. When we have a larger wavelength, well, what's going to happen is that if I have a single point, it's going to have a larger wavelet because of the larger wavelength. And if that happens, there's less room for other wavelets to interfere. You're going to get more of the spinning around the aperture. If I have a bunch of tiny wavefronts right here, well, all these in the center are going to interfere with each other. They're going to continue moving forward as if nothing has happened. You're only going to get bending on these outer edges. So you're not going to see very much bending at all, and it's only going to happen on the edges. Whereas this one, this is extremely curved. So bigger wavelength, more diffraction, smaller wavelength, less diffraction. Now those are the final takeaways on this lesson on interference and diffraction for mechanical waves, specifically waves that require a medium to propagate or move forward. So 1, can you describe and analyze situations involving constructive and destructive interference? Keeping in mind that interference is when two waves are in the same place at the same time, must be moving in some different direction to a degree, and constructive is when the amplitudes add, destructive when the amplitudes subtract. Can we describe how waves evolve as time progresses by utilizing Huygens' principle? Saying, okay, at some point in time, I look at all of the points on this wavefront, I generate all these different wavelets, I kind of fast forward in time a little bit, and I say, okay, this new wavefront is the tangent line from all of these spherically emitted wavelets. And lastly, can we describe diffraction, the bending and curving around openings or around barriers of waves, and explain why it occurs due to Huygens' principle, as well as identify factors that change the amount, how much bending occurs or not in a given situation.